Okay, okay. Hello, hello. Greetings from hello. There's Michelle F. There's Chris R. There's Yavi B. There's Maria Z. And I know that Maria was here before. Her video was blah, blah, blah. Okay. Wait, there's oh, I like the Michelle Q one of today. Right. Interesting. Okay. Wait, Arabic. Oh, coro. Arabic. Have we done that before? Okay, there's Alan L. All right, there's Cheska P. All right, sweet. Um, of course from Brooklyn. Well, hello to Brooklyn. Okay, let's don't even get me started. Okay, yeah, not the, oh, Queen. Well, Queens, really? No, okay. Yes. Okay, we're gonna get started in a second. Wait, who else did I not say? I haven't looked at the chat. Oh, yes, I did, obviously. Hello, Katie. It was great to see Katie yesterday live and in person, even though I was all postery. Hello, Michelle F. Good afternoon, she. Good afternoon, she. Three. Oh, that's a thing. Right. Good afternoon, Jada R. Good afternoon, Freddie R. Good afternoon, Allison M. Good afternoon, Brooke L. Good afternoon, Emily H. Good afternoon, Marilyn CH. Marilyn, yeah, you know what I mean. Because that's like one letter in Spanish, but your name's not Spanish, so I'm gonna keep going. Afternoon, Maria Z. Good afternoon, Stephanie I. There's no I in team, but there is a me backwards. Okay, hello, Michelle Q from Brooklyn. Indeed, I can't resist saying I was born in Brooklyn. My father was born in Brooklyn. His father was born in Brooklyn. My son was born in Brooklyn. I'm just saying. Okay, there are women in our family too, but they weren't born in Brooklyn. My mom was born in Brooklyn. Okay. Good afternoon, Alan. Good afternoon, Yavi. Hello, Queen. We like Queens too. We'll let it slide. Okay. Wait. Oh, thank you, direct chat person. Is that why okay, I did not. Okay, I did not post a game. Okay, I'll get to substance now. You're right. I knew something was wrong. All right. I did not post a game turn from Monday. I'll retro one in a minute just for so the numbers are right. Thank you. You're right. I'll try to fix that in a second. Also, okay, getting to well, good afternoon, Harrison. Sorry. Good afternoon, Paulina. All right, I'll get to quit. Yeah, all right. We're not gonna have the Brooklyn's Queens fight right now because it's like not even a fight. I mean, what? Okay. Um, Oh no, Alan's from Queen. Well, I have to take what Alan says seriously because he's like he's chooses his fights carefully. Okay. All right, we're not gonna do that now. Oh, guys, we're so not doing that now. Wait, but I'm not in my. Oh, you could come. That's funny. Okay, no, I'm not in my. If I were in my office, don't you think we've been having class for real? Like, I'm not in my office. Well, I am, but not that office. Um, Sorry. Okay, leave him the cold. No, I have no choice. Look, you go in, get a strawberry lemonade, but I'm not there. Okay. Your mom was born in Italy. Okay, that wins. That totally wins. I didn't know that. Okay, wait, we're gonna if everyone. Oh yeah, but not today. Oh, interesting. Yeah, the camera thing, that's still true. You could spread the word, but is it really today that would happen? You can't get that together today. Am I issuing that challenge? I don't know if today's today. All right, but no, if you ever did that, that's true. Okay, wait. All right, we have physics to do. Hold on, close caption. Hold on. Quick announcements. I promise. A lot of people have gotten their midterms back. In fact, the whole other like they're totally happening. You are getting them back. I promise. Some of you have not. I know, and it's not personal. It's not personal. But they really are happening. Like you definitely are you're getting them before next week. I promise. But still, if you haven't gotten one yet, that's true. You have like some people still haven't gotten them. They're just coming. They're coming. You can still write me questions about the stuff like that. We'll talk about the final and all that on Monday. Again, it won't be, it's not, okay, God, Michelle, no, I hate myself. I promise. I'm not even going to make a joke about that because the whole exam thing stresses me out so much. Wait, yeah. Are you able to submit game turns? Wait, hold on. No. The only bad news is that I'm always slow with them, which is bad. But at least this semester, I swear you're getting them back before you have to like. You'll know what's happening before you take your final. If you haven't gotten back yet, you're getting this week. I promise. Okay, wait. Oh, see, that's nice. But you will. You will. Okay. Wait. Oh, I see. Oh, I see what someone's saying. Okay, we're okay. Hold on. We're getting to like real things now. One sec. I Top 10 worst news I've ever heard. Oh my God. On that. Okay. Wait a sec. Okay, so the midterms are still coming, I promise. All the announcements and everything about in like preparation for the final will happen next Monday. Um, you all know, oh yes, I will accept like old homeworks, and the game, I will post a new game turn for Monday. As far as the regular game turns, as far as like the nightly 5 points, like turn one, turn two, those don't like if you haven't done a bunch of those or something, this is not the time to worry about those. Don't turn those in at the end of the semester. It just doesn't make any sense because you almost would have to be dishonest about it to do that. Like it, don't turn in it's not worth it. And they confuse me. But yes, when I say that all other regular homeworks can be turned in until the last day of classes, a week from today, when I say that, I mean it, and B, yes, all the special game things, the higher than 5 point ones, which all had a due date of like, I don't know, probably May 1 or something. Those I'll change the due, well, whether or not I change the due dates, the special games, like turning video on, showing Avatar, being Michelle Q, no, like all of those, yes, you could still turn those in as applicable, until the last day of classes. Um, I hope that's clear. So yes, those. Just the only thing you can't turn in anymore is like old regular nightly game turns, because that just doesn't make any sense to do that. Also be sparing about, like, I'll take, if you want to connect dots or fill gaps by next Wednesday. Obviously, I am not ever in a position to complain to people who, manage time in an exotic way. Like, I can't complain about that. But I would say, in this period of the semester, don't like focus mostly on like specific things that is unfinished business or unresolved or whatever, and then focus on the final. Don't spend the next 2 weeks just like trying to make a whole big pile of a million homeworks that you never thought about before and that you're just all gonna like copy now from your friend. Like, it's not, first of all, it's always really obvious when someone's doing that, really obvious. And second of all, it's really not worth it. Like, so yes, you can fill gaps and you can get yourself in order by the last day of classes, but don't start the whole semester now. And if you're going to, if you then start it by like really working on the final, which will count a lot more for you than something else that you could do. Okay, fine. Okay. Wait, there's one, and I will open up. It was great to see some of you at the poster presentations yesterday. I will open, you can remind me, I will open up a portal for that. If you were able to make it, that's terrific. Okay. Yeah. Oh, yeah. Oh, Katie just wrote that in the chat. Yes, I can. I'm probably not going to do it right at this moment, but yes, you can remind me and I will. So I'm going to make the greatest academic. No. And yeah, okay. I'm not even going to make jokes about that. I'm not saying you can't still try to cover a lot of ground in the next 2 weeks. Like, obviously a lot of us do things that way, but just choose your battles wisely. Okay. All right. I think that's, did I have any other logistics? So I want to get to physics. Right. Okay. So I'm sure there's something else I'll think of it, but yeah. All right. Wait, maybe I'll remind me, maybe when this is over, if someone wants to send me a text or an email, just remind me to fix the game turn that from Monday. I'll get myself confused if I try to do that now. And I will try to put a portal for, the posters. Okay. So what I'm going to do now is go back. I want to actually numerically do the calculation that we started yesterday. It's not super exciting, but it is super important. And it's like, it's hard to do without seeing it done once. So where we were yesterday, hold on, let's change it. We had this. So we had 2-point charges in a coordinate plane, right? One is a positive point charge, one's a negative point charge. And again, when we say point charge, that is what we mean. We mean a certain magnitude, a certain amount of charge, but focused or concentrated at like a Euclidean point in space, right? And so if we say positive point charge, what we really mean for you to picture is a huge number of protons jammed together in a Euclidean dot, right? And if we say a negative point charge, we mean a huge number of electrons jammed together in a Euclidean dot. Now, this doesn't happen naturally, as protons don't want to be next to each other, and they're usually trapped and protected in the nucleus. Electrons don't want to be next together, but we can make this happen either in the lab or certain conditions can force this to happen. Electrons can definitely be gathered together into a clump. And truthfully, realistically, sidebar, it's actually very difficult and very unrealistic to gather protons together in a clump because, again, they're usually protected. They're held together in the nucleus with neutrons and stuff like that. But really, if you want to know realistically in life, when people say there's a net positive point charge over there, what they really usually mean is that there's a huge concentration of the absence of negative charge. What it really means is there's like usually a whole, larger region containing many, many, many electrons, if that makes sense. Like really in the end of the day, okay, I'm getting off on a thing, but the way we create these situations or manipulate these realities is all through the electrons. That's why it's called electricity. Honestly, I mean, and that's, you may have heard the phrase free electrons in another science class. Electrons are the things that we can play with because they're out in the orbitals and they can be dislodged from atoms entirely, like we can ionize atoms, right? So it's always really realistically about clumps of negative charge or what sometimes people even call, oh my God, what do they even, charge holes, sometimes they call it, or is there something, I can't believe electron holes. So it's like electrons or electron holes is really what's going, anyway. So here we have that situation. And again, if we say that there's a positive point charge up there at coordinates 5, 4, and it's a positive point charge of +5 coulombs, just again, remember, that's an enormous amount of charge. It's not astronomical, it's not unrealistic, but it's enormous. 1 coulomb of charge, again, remember, is like 16 quintillion protons jammed together into that point, okay? And so then that's what we have here at coordinates 5, 4, and down at coordinates, sorry, is it at 5? Yeah, and over at coordinates 10, 3, we have the -2 coulomb charge, right? And so with the blue coloring and the red coloring in this picture, I mean, there's a lot going on in this picture. In the blue coloring and the red coloring, I'm just trying to show you that the blue coloring is the individual effect of that positive point charge. Like this, now those blue vectors, those faint blue vectors that are radiating out from the from the positive charge, those are field vectors. What we're trying to say there is that anytime you put a point charge anywhere in the universe, it immediately creates a field, right? At any time, which can be depicted or like pictured as a bunch of arrows everywhere in space in a pattern. Each arrow is a vector. And this is also, by the way, true of anytime you put a point mass anywhere in space. It immediately creates a whole array or a whole pattern of arrows everywhere in space, all in a very specific arrangement. And the idea behind those arrows is that we're saying the minute the arrows really capture what you might call a vector valued function. What we're really saying is the minute you put an object in space, there's now a function that exists that capturing or communicating the reality of that object that you put in space. What we're saying is the minute there's an object in space, by object, I mean thingy thing, like I mean a point of mass or a point of charge. The moment any point of mass is in space or any point of charge is in space, then for every single location in space that anybody ever names, like if you treat a point in space as an input into a function, then the output is that there's an arrow sitting at that point in space. The length of the arrow tells you the magnitude of the force that will be or would be exerted at that point in space onto any hypothetical test charge or test mass of one positive unit that could come along and exist at that location. So I'm going to say it one more time. Obviously, we're going to go back to the problem, but I really want to make this concept that I'm trying to describe to you right now is the concept of field. A field is a vector valued function. The input is a location in space, any location in space, like measured relative to some object, some point, some physical particle that is in space, right? So the input is like how far away and in what direction we are from some point source. That's what the input is. And the output is an arrow that will sit at that point in space that you're looking at. And the direction of the arrow says in what the orientation, the tip tail orientation of the arrow says what direction a unit +1 test charge would be pushed or pulled by the source if it were at that location in space. And the length of the arrow says how many newtons will it be pushed or pulled by as a result of the point source that's created this field that's in space, right? So every point is a source of field vectors that go everywhere in space. And notice, if you think about it, the pattern of the arrows from an individual point source, the pattern of the arrows from one point is always the same pattern. It's a radial pattern. The arrows fall in radial lines because what we're saying is whatever place you choose in space, so the blue arrows, in this picture, the blue arrows from the Q1, they're all pointing away from Q1, meaning that anywhere you pick and look, if you look at the tail of any one of those light blue arrows, what the tail of the arrow is trying to say is that if there were +1 coulomb of test charge sitting at the tail of that arrow, then that +1 coulomb charge would be pushed in the direction of the arrow and with the number of newtons depicted by the length of the arrow. So notice all the arrows are always pushing along a line that would connect the test charge to the source charge. The source charge is pushing you out along that line. And it's pushing you more and more weakly as you get farther and farther away. So the arrows get smaller and smaller as you get farther and farther away. Do you see? Okay, I'm over talking this as usual. But so the field is what would happen. The field is the force that would be exerted on a test charge of one positive unit placed at the tail of any of those arrows. If you're following this, then similarly, the red arrows all do the same kind of pattern. They're all radial and they're getting smaller. It's not even clear in the picture, but they should be getting smaller and smaller as they get farther away because the force is getting weaker and weaker as you get farther and farther away. How do I know that? Because the force is KQQ over R squared, R being the distance. Okay, so we're trying to say, so bottom line, if you understood or understand that force is measured in newtons, a force is something that one object would do to a second object. Field is what one object just does to space. And that's why field is measured in newtons per coulomb. It's the number of newtons that will be exerted on every 1 coulomb that could land in a certain location in space. Okay, so force is what I do to you. Field is what I do to space. Once you believe in fields, the way we say it is, until you understand about fields, you might say a proton pushes another proton. Now we say a proton creates a field. The second proton is in the field. The field exerts a force on the second proton. So what we're trying to do in this problem, to get back to it, is we're trying to say, okay, well, if every single object in the world does this, which we are saying, every bit of mass creates its own field everywhere, every bit of charge creates its own field everywhere. If we believe that, then isn't there more than one object in the universe? Yes. So like, what does all this mean? It means at any point, like, what does it mean if there's all these objects creating all these fields? Like, isn't it a mess? No, it's messy calculations, but it's not a mess. What we're saying is at any given point in space, the field that we all experience or could measure at any given point in space is the vector sum of all of the field contributions from all the dots creating fields all around in space. Now, so in reality, there's like many more than two charges, but we're just like first looking at a problem saying, well, how do you even combine the effects of even 2 points, right? And the answer is you combine their effects as a vector sum. So we're saying if we look, and obviously I'm trying to build myself back to the actual computation here, but I'm trying to give you a physical picture of what it is we're doing. If you pick the origin of this coordinate system, the 0, 0 point, I call that the location of interest. Like that's the location in space that we're interested in. Most textbooks or websites will call that the field point, meaning the point in space where we're trying to measure field, right? But let's be clear, we're just picking it as it's just the location that we're interested in. There is field everywhere in this problem, given that there's a proton sitting somewhere, there's an electron sitting somewhere. They're making field everywhere. We're focusing our attention on the 0, 0 origin point and saying, all right, well, just for example, what is the field there? So what we're asking is, what's the vector sum? What we're saying is charge 1 is placing a vector at the origin, and charge 2 is placing its own individual separate vector at the origin. We're saying the superposition of those two vectors, the vector sum of those two vectors, it makes one final vector, which will represent the actual field that we're experiencing at the origin due to those two charges. Are there other charges in the universe? Presumably, but we're like not taking them to either we're in a lab right now where we've isolated the situation and we're just looking at the effect of two charges, or we're just saying, yeah, there's plenty of other charges in the universe and they're all having an effect too, but they're all far away enough that their effect is much smaller, so we're not worrying about it, or we're just not even asking that question yet, okay? We're just zooming in and saying, what's the vector sum of these two dots as an example of how fields get created? Okay, I think that's it. So we're going to do the calculation. There was one other thing I was going to say. So, but yeah, literally at that dot, we're looking at the vector sum from the blue. Oh, right. And the red. Notice the vector E1 that's coming from Q1. Notice it's like an arrow that's pointing down and to the left and is really long. Like, why? Because Q1 is pushing down and to the left onto the origin. How do I know it's a push? Because Q1 is positive. Right? But then Q2 is pulling at the origin because Q2 is negative. And why? And negatives always pull and positives always push. Why? Because we're always asking what would happen to a positive 1 unit test charge at a field point. So we're always asking what would happen to a positive. So if the source is positive, it would push a positive, and if the source were negative, it would pull a positive. All right, I think that's all so I want to do the math. So anything last I wanted to say about this? Okay. Yeah, all right, so let's do the math. So we started the math yesterday. We said, all right, we're going to zoom in on these two individual field contributions, E1 and E2. Right, so we zoom in. E1 is going down and to the left, or in other words, sort of southwest. And so we divide it into its components. We say it's got a horizontal component that is the cosine portion times the magnitude of E, and it's got a vertical component that's the sine portion of E. So, and what we're gonna do the same thing to E2. Whoops. We're going to do the same thing to E2, take its components, individually, and we're going to add up all these components. So the method that we're doing is here on this sheet. That's like the roadmap. Now let's fill in the numbers to show you how to get the numbers. So I'm going to go to so I'm going to go to the next page. I'm going to zoom in again. I'm just going to look. So here is. Oh wait, let me say one last thing. If you're looking at this roadmap, where did it? Wait, why did E2? Why did I draw E2 twice? Hang on one second. I don't know what this is. Hold on, sorry. E2 is going up and to the right, right? This is. Sorry about that. And someone's here. Sorry. Okay. If you look at the diagram, E1 is going down and to the left, so I've zoomed in on it. And then E2 is going up and to the right, so I've zoomed in on that. So we're going to get all those individual components and we're going to add them together. And so one more thing I'm going to say is what we're physically to picture what we're doing, we're adding these two vectors. So that means if we're trying to picture the combined effect, we would place them tip to tail. Oh, was it? Oh, okay. Thank you. And that, okay. Wait, I'm looking at the, huh, thank you. Okay. I guess it was, but I guess I labeled it wrong. Okay. Oh, yes, 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 you're right. That very good, Maria. Okay. Yes, yes, yes. Okay. Okay. So I'll draw it again in a second. You're right. That's good. Let me show you where that idea came from, though. No, very good. So look, if you place these two together, tip to tail, which is what you do when you're adding vectors, right? It's like if you're walking, if you walk that way and then you walk that way and you want to know overall, where did you walk? Well, if you try to picture what happened, what your overall displacement is, you did one thing and then you did the other. So you would place the second arrow beginning at the end of the first arrow, right? Like whenever we're adding vectors, we place them tip to tail. So, right, this, when we're literally adding them, like this diagram shows you what the arrows are. So like a free body diagram, they're both being depicted as emanating from the origin. We're saying at the origin, you would simultaneously be, you'd be pushed down to the left, southwest, and at the same time, you'd be pulled up and to the right, right? So this is a little subtle, but this diagram is showing you the facts. Okay, sidebar, this came up in the midterm for a lot of people. Just, okay, slight sidebar, but for the sake of the final, like whenever step one of any problem that you're solving, step one is always diagram fact pattern. That means that's even before anybody asks you to draw any graphs specifically, or any free body diagrams, or any like analytical tool diagrams. We always say, when you're solving a problem, so again, sorry, I'm shifting gears for a second for everybody who's like still either trying to figure out my comments on their midterm or trying to get ready for the final. Like word to the wise, pro tip, I'm saying, whenever you have a physics problem, even no matter what the person's asking you in the physics problem, first they present you with a bunch of facts, right? Like the situation. I'm saying as a physicist, the first thing you do is you draw a picture depicting those facts. That this is important, right? Like this is like when you're doing a lab in any other science class or anything, like first you collect data, right? In a lab or in an experiment or in research or in Prism. First you collect data, then you go around like doing analysis and then you do like findings and results and stuff like that. So I'm saying when you solve a physics problem, same thing. First, you draw a picture of what the data says, of what the data say, like what the facts are. So, and then you proceed to, and then you write down, look, what is the question and stuff. Then you proceed to start to try to analyze the facts and put them together and do like techniques like graphs or free body diagrams or stuff like that. So I'm saying here, and this is really, I think, confusing to people when it comes to fields. This picture on the board right now, that's like my DFP. That's my step one, where I'm just laying out the situation. I'm not doing anything there. I'm just laying out the situation. So the situation is that if I were sitting at the origin, I would simultaneously feel pushed that away, and I would feel pulled that away. That's the situation. Those two arrows are like a free, they're just, they're both showing that they're both relevant to the origin. So their tails are both at the origin. But now, now I'm starting to solve the problem. Now I'm asking the question, what is the combined effect of those two arrows? Like, what's going to happen to me? In what direction? If I were a +1 Coulomb of test charge, like, where would I be pushed or pulled, and how hard? So then I start breaking up those arrows into their components. And then, I say, oh, okay, like I say, if I want to see what's going to happen, I'm going to feel the tip to tail combined effect of these two arrows. One is long and going southwest. The other is short and probably less steep, sorry, and going, northeast. So if I place them tip to tail, the combined effect of them that I'm trying to solve for would be one final arrow completing the triangle that goes from the original tail to the final tip, right? I don't think I drew that as. Well, yeah, okay. I'm obviously not drawing it really to scale, and that's a problem, but I'll try to be a little bit more to scale here. So this is a new triangle. This is not the thing I drew yesterday or erased. I'm basically showing you where the thing that I drew yesterday that Maria and erased. So this, what I'm saying is, this is a depiction of what's going on if I place the two arrows tip to tail. Their combined effect, it will be a final arrow that will still point down and to the left, but will presumably be like a little shorter, right? Because the push from the proton is dominating. It's a much bigger arrow. So right? So it's going to be it. I'm over talking this, but the big arrow is going to dominate over the small arrow. So I'm going to be, in the end of the day, I'm still probably going to be pushed south, and I'm still probably going to be pushed west, but less so than the E1 would have had me be. Like, the effect of the E2 is going to be to sort of unwind a little bit of the strength of the E1, right? E1 pushes me very hard to the west, but E2 pushes me a little bit hard to the east. So the net effect will be I won't be pushed as hard to the west. And same thing with the ups and downs. So the final answer I'm going to get is going to presumably be an answer that pushes me somewhat south and somewhat west. And this is a depiction of what my final arrow should look like when I'm all done. And I'll use it as a check to see. And then the part that I had accidentally erased that Maria just pointed out is, like, that combined effect will be, like, where will I get it from? How will I know what the exact numbers are? Well, that combined effect will be the Pythagorean sum of the x answer that I get when I add up the two individual x's plus the y answer that I get when I add up the two y answers. So yes, Maria is right. Like, the triangle I had there was not a mistake. It was not a mistake. That's good. Thank you for your support. But, like, if I do everything right, and I will now, I don't know why I'm spending so long postponing numbers. Because the numbers scare me as much as they scare you, maybe. I'm saying at the end of the day, after I get all these numbers that are going to go into this chart, I'm going to get like 4 numbers are going to go into a chart. I'm going to add them up. I'll end up with 2 big numbers. They'll make a big triangle. And the end of the day, this brown thing right here should be the answer. That should be the hypotenuse of that triangle, and that should be the answer to my whole field calculation. And if I've done this right, it should, like, resemble, like, if all of these things were drawn to scale, these two things are just 2 different depictions of the same thing. And really, what all this is saying in the long run is if my final answer is not pointing southwest, I've done something wrong. I mean, that's really what. And if it's not pointing southwest, but somehow smaller than the original E1, then I've done something wrong. All right, so enough postponement. Let me, but that was great, Maria. Thank you. I totally, you should definitely submit that to a portal. Okay, so where do I get these numbers from? What are these numbers? Okay, so I'm zooming in again. So I'm going to zoom in again on E1. E1 looked like this. It has an X component. It has a Y component. So this is like E1X, and this is E1Y. This is theta. So E1X will equal E1 times cosine of theta 1. So I'm going to solve for that first. Now, where do I get that? Well, what is that? E1X will equal KQ1, sorry, yeah, KQ1 over R squared times cosine of theta 1. Notice I'm just, so I'm solving for magnitudes. I'm solving for magnitudes now. So you notice that all the fancy vector symbols and everything go away. I'm not, the directions I already can see in my pictures. So now I'm just solving for the lengths of these triangle sides. So I don't need the vector symbols right now anymore. I'm just now plugging into that equation, the field equation. It's the field, the Coulomb's law for the electrostatic field. It's field that I'm calculating. So there's only one, it's not KQQ over R squared, right? It's just KQ over R squared. Force is what one thing does to another. Field is what one thing does to space. So the field equation only has the source charge in it. And also, just for the record, I just want you to get used to the fact that there's two different ways of writing this. You can write K as K, or you can write it as 1 over 4 pi epsilon naught. Ultimately, the second way is better, but it takes some getting used to, but they both mean the same thing. So if I plug in numbers now, what I'm saying is E1X equals approximately 8.99 times 10 to the 9th, which I'm going to round to 9 times 10 to the 9th Newton meter squared over Coulomb squared, okay, times Q1. Q1 means the source charge Q1, like the amount of coulombs, which I believe was positive 5 coulombs. So I'm just going to write 5. I'm just writing the magnitudes now. I don't have to worry about positive or negative now because I've already taken that into account in all the pushing and pulling in the diagram arrows, right? So the Q1 is 5. Just okay. I'm just trying to get myself room. So the Q1 is 5. Now, what's R squared? Well, what's R? R is the distance, literally the distance from Q1 to the origin, the total distance. So in other words, the hypotenuse of that, well, what it is this. Remember, the coordinates of Q1 are 5, 4. So the whole distance is the square root of 5 squared plus 4 squared, right? The whole distance, R, is the square root of 5 squared plus 4 squared. But the equation, the field equation, says that we want R squared. So it's the square of the square root. So I'm just writing it as 5. Oh my God. 5 squared plus 4. Right? And then it says to put in the cosine of theta. So you might think, oh God, the cosine of theta, like, first of all, I have to solve for what theta 1. So you might think, I might think, oh, I have to solve for theta now and then take the cosine. That's how do I get the theta? And then you might think, oh, because you're not given theta, but you might think, oh, I can get the theta because I could do like a SOHCAHTOA thing, like inverse or like arc cosine or something. And yes, you could do all that. But if you're going to do SOHCAHTOA anyway, you could cut to the chase and realize that the cosine of theta equals the adjacent over the hypotenuse, which is to say the cosine of theta 1 equals like x1 over r1, right? So we can cut straight to the chase. In other words, cosine of theta 1 equals 5 over the square root of 5 squared plus 4 squared. You see, and you may want to put in the chat if you're still with me, if you were up with me until that moment, like it's going to happen a lot. So don't let it go. If you don't get what I just did, put it in the chat. But I'm going to go to the next page. I'm just going to rewrite now. I'm saying so far, this is all a computation to get one component. Once you get used to it, then you're used to it. But we are going to do this 4 times, but not as slowly each time. But this is the idea of getting a component. We're saying it's, sorry. So it's 9 times 10 to the 9th times 5 times and that first 5 is the charge. It's not from a coordinate, but then it's the x coordinate over this. So this is the x component of thank you, Katie. Okay, right. Okay. How did I get right? So okay, let me write it. So what I just think that I wrote what I just solved for was this. Right. So k is not times 10 to the 9. Q is 5. R squared is 5 squared plus 4 squared. So I'm saying, but then how did I get the cosine of theta 1? Like, I'm glad Katie is asking, and maybe other people are too. I'm saying this whole piece right here is cosine theta 1 because I'm saying, well, so here's the triangle again. Wait. Here's the triangle again. Now I'm saying that's theta 1 there, right? But I'm going to zoom in right now on like here is Q1 right here. And here is the origin, right? And the coordinates of Q1 are 5, 4. So this side is 5 units long, and this side is 4 units long, right? So I'm saying that the cosine of the angle, and the 5 and the 4 I just got from the facts of the problem. Like Q1 is at the coordinates 5, 4. So cosine of theta 1 has to equal the adjacent over the hypotenuse of this triangle. So it has to equal the size of the x side over the whole hypotenuse, which is the whole distance. So the cosine of the angle has to equal literally 5 over the whole distance. And what is the whole distance? It's Pythagorean sum. It's the square root of 5 squared plus 4 squared. Let me pause for a second, because I honestly, I think that is, in a way, like the hardest part of this whole thing. And if it goes too fast, the whole thing is so I want to ask honestly, Katie, does that, or well, yeah, Katie, does that help?
I want to say this makes more sense. I'm just kind of confused on where you got x over r for the equals cosine.
Okay, fair enough. No, I totally appreciate your honesty and your clarity. Well, I'm saying in that triangle, if we agree that cosine is adjacent over hypotenuse, then in that triangle, the side that's adjacent to the angle is the x component of that triangle. It's the horizontal leg of that triangle. And that triangle is depicting, like, literally that triangle is like how it's like, hold on. That triangle, okay. that triangle, I don't want to get this even more colorful, but that triangle is, I'll do it with highlighter. That triangle is this. Like the triangle I'm drawing right now. I'm saying Q1 is up here at coordinates 5, 4. It's to the above and to the right of the origin. So the line that connects Q1 to the origin is the hypotenuse of that triangle. And then the two legs are just like, well, mean how far over is Q1 from the origin and how far above the origin is Q1. So by X, I mean, like, so this is what I mean by X. And this hypotenuse is what I mean by R. Because R, when you're talking about fields, means the distance from a source charge to the location of interest. That's what R means, like the distance from whatever's causing the field to the place that you're measuring field. That's what R means. So R is that distance from Q1 to the origin. And X is the X component of that, and Y is the Y component of that. Does that make so? X is the X coordinate. And what am I making any sense or no? Oh,
It made a lot more sense. It made a lot more sense once you put it up to the graph.
Oh yeah, and I just saw your chat. Sorry. Okay, great. Okay, awesome. Okay, good question. I'm glad. Okay, and again for no, thank you. Okay. Okay, so cool. So right. So from here on in, the basic trick that Katie's asking about the for what it's worth, is this worth saying? Hold on, let me think for a second. What we're really saying at the end of the day is that the field that I create at a certain distance from me is very much based on, very much determined by the displacement from me to the point in space away from me. Like, we are saying that everything in life creates a field, which is a bunch of vectors at all points. And if you want to know if I'm the one making a field, and you want to know how strong the field is at a certain displacement away from me, then the field magnitude and direction is determined by the displacement away from me. Like, there's a function, and the input of that function is the displacement away from me, which means distance and direction. And the output of that function is the field. So, all right, I'm over talking this again. I mean, I think she's got it. I think you, but all right. So, hold on. Let me just think for a second if this is worth saying. No, it's probably not. All right. So from a computational standpoint, the big thing that Katie was just asking about, the big trick of these computations is each field component is the field equation times cosine or sine of the angle. But what we're trying to say is if you really picture these triangles correctly, you can you could save yourself a couple of steps. And instead of calculating angles and then taking sines and cosines of them, realize that the cosines and sines of angles are just ratios of the triangles that you're already looking at. All right, okay, so here's my component. My E1, my E1x is all these numbers. So I'm going to write it one more time just to do the math. So E1x is 9 times, it's approximately 9 times 9, 9 times 10 to the 9th times 5 over 5 squared plus 4 squared, all times 5 over square root of 5 squared plus 4 squared. So in other words, 5 squared plus 4 squared to the 1/2 power. So I can simplify this a little bit. I can say it's like it's like 9 times 25 times 10 to the 9th power. So in other words, 225 times 10 to the 9th power, right? I'm multiplying out the top. I'm trying to do as much as I can without a calculator so I can picture these numbers. And the bottom is, not coincidentally, it's It's that same term, but multiplied to two different powers, 5 squared plus 4 squared times 5 squared plus 4 squared to the 1/2 power, right? So what is that all in general? That's 5 squared plus 4 squared to the 3/2 power, right? Like that seems weird, but like you imagine that this pattern is going to happen with every one of the components. So now I can put it in more proper scientific notation, 2.25 times 10 to the 11th, all over 25 plus 16, 41 to the 3/2 power. Right now, we're almost getting to the point where I can't do it in my head or where you can't. But what does 41 to the 3/2 power mean? It really means the square root of 41 cubed, right? Or 41 cubed square rooted. So in other words, that you can do on a calculator, 41 to the 1/2 power. And you can literally do like 41, like caret 1.5. And so you, yeah. So you get, oh, sorry, wait, one exponent error here. Sorry. This is supposed to be, this is supposed to be, to the 10 to the 11th. Sorry, no, I knew something was wrong. Like 225 times 10 to the 9th is really 2.25 times 10 to the 11th. So the numerators, I knew I dropped an exponent somewhere, 10 to the 11th. So you do 2.25 times 10 to the 11th divided by 2.63 times 10 to the second. And you get, okay, now we're talking like 8.56 times 10 to the 8th. What is that? Like my answer for one component so far is like approximately 8.56 times 10 to the 8th newtons per coulomb. That's not the answer to the whole problem, but it's like sort of the hardest piece. What this means so far is I'm saying if I were just sitting at the, like, and you want to be able to picture this in your mind, like we're 1/4 of the way through the calculation, just to be clear, but it's all repetitive from here on. But we've got one number to put in our chart. What we're saying physically is if you were at the origin, if you were a 1 positive coulomb of charge at the origin, and you only felt and Q1 was the only point charge in the lab, you would feel Q1 push you this hard to the west. This is just a computation of how hard every 1 coulomb of charge, every 1 coulomb of positive charge located at the origin would be pushed to the left due to only Q1. Okay, again, I'm trying not to Right. So someone just put in the chat. Right. Like all we have so far, this is totally disregarding, as someone just said in the chat. We're not up to Q2 yet. This is just what is technically known as the field contribution from Q1 on the x-axis. All this is what Q1 is doing to the origin along the x-axis. So correct, yes. It does not take into account Q2. So then next, we're going to calculate the y component of what Q1 is doing. Then we're going to separately compute the x component of what Q2 is doing, and we're going to separately compute what the y component of Q2 is doing, and we're going to put them all together. And so, yes, this is a piece of physics that's important. Like we're just doing math, right? But this is called superposition. We are believing when we do a vector sum like this, what we're believing is that the combined effect of Q1 and Q2 can be figured out or predicted by just seeing what each one of Q1 and Q2 would have done in isolation and adding together those effects. We're believing that that the vector sum of Q1 and Q2 onto the origin, we're believing that the vector sum we're literally believing that the whole is equal to the sum of its independent parts. Again, I could rabbit hole on that. Like that's a whole deep idea. And in other words, we're saying that what Q1 is doing, what Q1 is contributing to this total is not affected in any way by the presence of Q2. Q1 does not know that Q2 is there, and Q2 does not know that Q1 is there. The origin knows that both of them are there. That's what we're saying. That Q1 doesn't, whatever influence Q1 has over the origin is not like messed up somehow or interfered with by the presence of Q2. Okay, so that is a really good observation. So we're just independently computing the pieces and then adding them all together. So this is piece one. This is what Q1, how hard Q1 would push to the left on every 1 coulomb of charge that could ever land at the origin. And okay, last thing I'm going to say about that, note that's what we mean by newtons per coulomb. Newtons per coulomb. It means if 1 coulomb were sitting at the origin, it would be pushed exactly this hard to the left. But if 2 coulombs were sitting at the origin, which they totally could be, then they'd be pushed together, they'd be pushed twice as hard. It goes back to the issue from Monday, right? And if 3, then 3 times as hard. This is on every coulomb that might arise. So it's a prediction. This is happening whether there's nothing or everything at the origin. That's why this is field, not force. This is the information sitting at the origin, waiting for something to come along and experience a force. Okay, so I'm just going to keep doing the math. But it's not it's a powerful notion. So that's E1 sub X. So now of course, I'm going to try to go a little, we have, 18 minutes. I'm going to do each one of these pieces now the exact same method, but I'm going to go faster and faster. You could still stop me, but please understand that I'm just like, now it's like a pattern. Like now we get E1X. I'm sorry, we just did that. Now we do E1Y. So what's that going to be? That's going to be K Q1 over R1 squared, just like before, but now times the sine of angle 1. Okay, so that's the only difference. We're going to put in all the same numbers, but do the sine component now. And I'm not putting in negative or positive signs because my diagrams already make it clear to me. This one is going to be a push down. I can see in the triangles. So it's 8, so it's like 9 times 10 to the 9th. The Q1 is still 5. That means 5 coulombs of charge over what is still 5 squared plus 4 squared, or in other words, 41, times now the sine of the angle. So the sine is the opposite over the, oh, okay, cool. Okay, got you. One second. Oh, okay, sorry, so just left. Okay. So the sine of the angle is the opposite over the hypotenuse. So the opposite now is no longer 5, it's now 4. But the hypotenuse is still the same. Right, so it's literally the same thing as before, not only the same method, but the same numbers, except we change that second 5 to a 4, because we're now doing the y coordinates. So we get 100, 20 times 9 is 180, so we get 180 times 10 to the 9th over 41, because it's still 41, like 25 plus 16 is 41, to the 3/2 power, right? So that's 100. So it's all the same except where it's different. So now we say so now we get like 6.84 times 10 to the 8th newtons per coulomb. Okay, so that's that, all right? So that's the y component of the Q1. Now we go to the Q2, or the effect of the Q2. So we go to E2X. So what's that? Well, again, it's KQ2 over R2 squared times cosine of angle 2. Now I'm not gonna draw this again, but you had, flip back and see we're looking at the other triangle now. So now Q2 has a charge of 2 coulombs. You might say it's -2, and you'd be correct, but I'm not putting the negative signs in because this is all magnitude. When I look at components, I'm just looking at magnitudes. We've already taken into account the negative charge when we decided that this is now a pull rather than a push, right? So our diagrams make that clear, but I'm putting in the magnitude. So the magnitude of the second charge is now 2. And the R, okay, is R2, the distance from the second charge to the origin, right? And that distance is a much bigger, it's like the coordinates were 10,4, I believe. Coordinates, I believe, were 10,4. 10,3, excuse me. Okay, the coordinates were 10,3. So the total distance is 10 squared plus 3 squared and square rooted. So the total distance would be the square root of 10 squared plus 3 squared, right? But in the equation, it has to square that distance. So I did. Now the cosine is the adjacent over the hypotenuse of that angle. The adjacent is 10. This is back to Katie's question now. The adjacent of the triangle is the horizontal component. The x component is 10. And the whole hypotenuse is 10 squared plus 3 squared, square rooted, right? So same pattern as before. So now we have 180 times 10 to the 9th in the top. And in the bottom, we have 10 squared plus 3 squared, excuse me, which is 109 to the 3/2 power, right? So we have 1.8. It's a good physics habit to just try to do as much as you can in your head for like set things up and keep arranging things until you like are forced to use a calculator. And obviously that point comes earlier or later for different people, but it's a really important physics habit to do that, to postpone, especially in thick computations like this. And especially if it were an exam. And again, like obviously I keep saying your final exam will be shorter and you'll have choices, but this problem here that we're spending all this time on is generally one of the choices on the final exam. Like I don't know whether you'll choose it or not, but it definitely, whatever, you get my point. So it's a good habit in physics when you have thick computations like this to just keep arranging and cleaning them up and postpone that calculator moment for as long as possible, because it's partly a macho thing, I suppose, after a while, but it's really about that we're trying as physicists to have a feel for these numbers. We don't just want to be blindly putting in things into the calculator so fast that whatever it spits out, we're just going to trust, because we don't know if we're doing the calculator that well. Right? So what you want to do is keep looking at the numbers and try to have a sense of the numbers so you know more or less what kind of numbers you should get at the end. And so then when you press into the calculator, it's like just making it more precise, the part that you can't do. But it gives you numbers that should land in a slot in your brain that you already were picturing. So you're always triangulating yourself. Anyway, so 1.80 times 10 to the 11th on the top, and 109 to the 3/2 power on the bottom. That should, like, for example, I'm going to say 109 to the 3/2 power. Can I do that in my head? No, I can't do that in my head, but I could say what that's like 100. I mean, it's 109, but that's like 100 to the 3/2 power. What does that mean? That means the square root of 100 cubed. That's what that means, right? 100 to the 3/2 power should be about 1,000. I mean, no, it's exactly 1,000. So 109 to the 3/2 power should be bigger than 1,000, but not be like 15,000 or a million, right? It should be a number in the thousands. So I have a sense before I type in especially doing weird things like this on a calculator that I'm not used to make sure I did it right on the calculator. I'm expecting a number that's like bigger than 1,000, but smaller than like 15,000 or something. So, right, that's what, anyway, whatever. That's physics thinking. And in my calculator, I literally just type 109 caret 1.5. Right, I'm doing it to the 1.5 power. Okay, and what do I get? I get 20 million. No, I get like 1.14 times 10 to the third, which is like, what is that? That's like 1,140, like a little bit more than 1,000. Oh, I'm not crazy. Yes, I am, but not for this reason, right? Okay, so then we do literally Enrico Fermi, the great Italian-American physicist who won the Nobel Prize and who worked on the atom bomb, and like I think he was depicted in that movie, Barbie. No, just kidding, Oppenheimer. He was a great physicist and a great teacher. And he was a monster calculator in his head. I mean, he could calculate like he was head and shoulders even above all his contemporaries who worked at Los Alamos and all of that. There's great stories about him. But anyway, but his whole point, I mean, he was an amazing calculator, but because he had such a feel for numbers and he was always trying to reduce numbers to a feel level before, and his whole thing was you never ever start a calculation until you're already pretty sure you know what the answer should be. Like that's physics thinking. Okay, so here we get 1.57 times 1.58. And that's what scientific notation really helps you do after a while. At first, everybody hates it. I know that. But after a while, it actually helps you have a sense of the numbers. But okay, anyway. So this is now E2x. E2x. So we have one, and it's newtons per coulomb. So we get one final number now, E2y. And that will be 9 times 10 to the 9th times 2 all over 109. Well, all over 109 times 3 over 109 to the 1/2 power, right? You see, oh, and I skipped something, didn't I? No, I didn't. Yeah, right? So that's the pattern. So 6 times 9 is 45. So 45 times 10 to the 9th all over 109 to the 3/2, which we've already figured out is 1.14 times 10 to the 3rd. So 4.5 times 10 to the 10th all over, 1.14 times 10 to the 3rd. And here too, I should have been saying this all. I look at this and now I'm expecting some kind of like 3 times 10 to the 7th kind of number, right? Like I don't know exactly what it is, so I am trusting electronics, but like I'm expecting something to the 7th. I mean, something to the 7th power. And if I get something else crazily different from that, then I know I've done something wrong. And not just okay, so 3.9 times 10 to the 7. Okay. All right, we have 7 minutes. So now I've got newtons per coulomb. So that's E 2y. So now I have 4 components. Now the idea is to put them together, right? So I make that chart. We're almost done. And then we're almost done. So the chart is we're adding E1 to E2, but we're adding by components. And this is also goes back to what somebody put in the direct chat. When someone said in the direct chat, oh, so is Q1 like disregarding Q2? And the answer is very deeply yes, like super good question. Similarly, the whole presumption of all this is that the x-axis disregards the y-axis. The whole idea behind all of this is that every coordinate system is its own world of physics. The laws of it's all Galileo. The laws of physics are the same in all inertial reference frames. That means all coordinate systems. And the x-axis is a coordinate system unto itself, as is the y-axis. So like we're saying physics is just happening on the x-axis, while independently, yet simultaneously, physics is happening on the y-axis, right? So that's why we can make these charts like this, because we're saying like each piece does not know that the other piece is happening. So then the final result is the combined effects of all these independent yet simultaneous pieces. It's very deep. You should like physics. You should give it a try sometime. Really, I highly recommend physics for their patients who chew gum. Okay, so we just fill in the numbers now. And now I'm going to pay attention, and we're just going to add. We're literally adding. I don't care what the minus signs or whatever say. We're adding because we want the combined effect, right? We're going to add the x components. We're going to add the y components, but some of those components might have negative signs, right? But that doesn't mean we're right. And how do I know? I look at the triangles. I look at the directions. Like E1x. So now I'm filling the number E1x. Hello. E1x was like 8.56 times 10 to the 9th. So I'm going to put that in the chart, 8.56 times 10 to the 9th. 10 to the 8th, I mean. But it was going to the left, so it gets a negative sign. I mean, it was going to the west, so it gets a negative sign. And then E1y, right? E1y was 6.84 times 10 to the 8th. 6.84 times 10 to the 8th. And it was going down, so it gets it was going south, so it gets a negative sign, right? And these are all newtons per coulomb. Then E2x was 1.58 times 10 to the 8th. But it was going east, so it gets a positive sign. And finally, E2y was 3.95 times 10 to the 7th, a lot smaller. And it is going north, so it gets a positive sign. So now I'm going to add. So I'm adding down. So negative 8.56 plus positive 1.58. In other words, so negative 6.98 times 10 to the 8th. And the other, and then I add down, so, and be careful with this one, because the exponents are different. So basically that 10 to the 7th is barely going to make a difference in terms of the 10 to the 8th. But like if I don't get a number very similar to 6.84, if I don't get 6.74 or something like that, or times 10 to the 8th, and I've done something wrong. Right. So I get like negative 6.45 times 10 to the 8th, right? Because I hope you understand, because the exponents are different. Okay, so now what do I do? We have 3 minutes. What do I do with this? Okay, this was the thing. This goes back to the triangle that I accidentally erased that Katie pointed out what it actually was supposed to be, is this. Like now I'm saying at the end of the day, if I'm sitting at the origin, I'm going to get pushed. Every coulomb of positive charge that might be sitting at the origin gets pushed to the left. Every coulomb gets pushed to the left with 6.98 times 10 to the 8th newtons of force, and it gets pushed down with 6.45 times 10 to the 8th newtons of force. So I draw a big triangle. I always draw my horizontal first, and then from the tip of the horizontal, I draw the tail of the vertical, and I draw it somewhat, these legs will be somewhat similar because the numbers are somewhat similar. So I go like that, right? And this is 6.98 times 10 to the 8th, and this is 6.45 times 10 to the 8th. So the overall answer I'm looking at, the thing that we predicted with like 45 diagrams at the beginning, and I know there's 2 minutes left, the overall answer would be this hypotenuse right here and this angle right here. So the overall answer, the overall answer will be the Pythagorean sum of those two legs. So 6.98 squared plus 6.45 squared, all square rooted times 10 to the 8th, right? So like 9.50 times 10 to the 8th newtons per coulomb. Like this is the answer at an angle of the arctan of those two numbers. Right, tan to the -1 of 6.45 over 6.98. And those numbers are very similar, so it's going to be an angle that should be close to 45 degrees, right? Yeah, like so 42. So theta will be approximately 42.7 degrees southwest. So this is my answer. If I'm at every coulomb that's at the origin would be pushed with approximately 9.50 times 10 to the 8th newtons of force at an angle of 42.7 degrees southwest, and that is 1:30. So I will see. So text or email me. You'll get your exam soon. Have a great week. I'll see you Sunday. Blah blah blah. Thank you for your. Have a great day. Have a great day. Thank you for your everything. Bye. I mean, yes. Goodbye, Michelle. Goodbye, everybody. Okay. Have a
Bye,
great day.
Professor.
Bye. Awesome. Awesome. Thank you.
I just have a question for you really quickly.
Yes, absolutely. I'll turn off the recording.